Hello, this is Abhijit and you are watching my YouTube channel AB Study Circle. In this video, we will discuss about closed system work for various processes. So, let's start. Closed system work for various processes. First is constant volume process, which is also known as isochoric or isometric process. In some book it's isochoric, or in some other it's isometric. So for closed system work, we have earlier defined how the closed system work is derived in thermodynamics, right? Let's have the PV plot right. As we have, it's a constant volume process, means the volume will be constant, right? So it will be in this fashion. This is the two states, state 1 and state 2, and the process will have a constant volume, right? But the pressures will be different. Now for closed system, the work was defined as integral P dV. As volume is constant, dV is 0. Therefore, work is 0 for constant volume process. Right. A physical example of constant volume process is in this way. This is a beaker. We have a Bunsen burner to heat up this beaker. Right. It's a piston is having in this arrangement, and there are some stoppers which will stop the piston from moving up. So it will have a constant volume, and this represents a constant volume process. Okay. The second process is isobaric process, which is also known as constant pressure or isobaric process. So again, the PV diagram, PV plot. As work is shown under the PV curve. So as it is a constant pressure process, we have a process like this. can be from 1 to 2 or 2 to 1 accordingly. And when it is like this, we have V1 and V2 corresponding to process. This for state 1 it's V1, for state 2 it's V2, and the pressure is constant. Right. So W is equal to integral P dV. As P is constant, we can take the P out, and integral dV, we have the limits from V1 to V2. So we can get P is V2 minus V1. So W is P into V2 minus V1. Right. For a physical example of this process is like this. It is a piston cylinder arrangement, and bottom we have a Bunsen burner again. Right. There is P is the isobaric process. In this process, the components are P atmosphere plus pressure of the piston is equal to P1. Means this P1 will work against the atmospheric pressure and the pressure due to this piston. Right? And it's a constant baric process. Example of a constant baric process. Okay. Now we have a third process known as constant temperature process, which is also known as isothermal process. Isothermal processes are those processes which are carried out very slowly, means at every point from one state to another, the process, the temperature is constant. Right? So let's get the work done for constant temperature. For ideal gas, we have PV is equal to mRT. Good. As T is constant, we have PV is constant because M and R are already constants. From here we can have P is equal to constant by volume. Right? That means P1 V1 is equal to P2 V2. We have this. Now, what is the initial or the general work done formula? That is integral P dV. The differentiation limits are integral limits are from V1 to V2, right? So we can write P as constant by volume into dV. V1 by V2, C by V dV. Right. As it is constant, it can be taken out. V1 by V2 dV by V. It is C ln V2 by ln V1. We have differentiated it. It is natural log V2 minus natural log V1. It will be ln V2 by V1. Yes, we have got it. W can be P1 V1 ln V2 by V1, or it can be mRT1 ln V2 by V1. Again, we can have, from this we can have P1 by P2 is equal to V2 by V1. So we can write this as mRT1 ln P1 by P2. So this formula of work can be used when there is a constant temperature process is carried out, right? So from this equation, from this formula we can observe some points, such as, see, we have this PV diagram, we have this process from 1 and 2. Suppose this process is from state 1 to state 2, right? As the volume increases from state 1 to state 2, we can say that it's an expansion process, right? When it is like this, means V2 is greater than V1, okay? Then V2 by V1 is greater than 1, right? And we have the work done formula as P1 V1 ln V2 by V1. As this is greater than 1, we say that the work done will be positive. Work done will be positive. But when the process is like this, one to two, it is a compression process, means V1 is greater than V2, that means V2 by V1 is less than 1. Then our formula, that is P1 V1 ln V2 by V1, this is less than 1, that means work done is negative. Means what we have observed from these two example is that when the process is of expansion, the work done is positive. That means the system is doing work. But when there is an expansion process, the work done is negative. That means work is done on the system. Okay. So we have another process, that is adiabatic process. Adiabatic process is that process where there is no heat interaction between system and surrounding. For adiabatic process, we have this law, that is PV to the power gamma is constant. What is gamma? It's nothing, it's adiabatic index. And for air, gamma is 1.4. And you should remember, gamma is always greater than 1. Right. Again we have the formula, W is equal to integral PdV. But from PV to the power gamma is constant, we have P is equal to C gamma V to the power gamma, C by V to the power gamma, right? So the work done formula will change to C by V to the power gamma dV. From this, C is constant, we can take it out from the integration. dV by V to the power gamma, we have C V minus gamma plus 1 by minus gamma plus 1. Limits are V1 to V2. From this, we have C by 1 minus gamma plus 1, that is V2 by V2 to the power gamma minus V1 by V1 to the power gamma. From this, we can have 1 by minus gamma plus 1 P2 V2 minus P1 V1, right? So work done will be P1 V1 minus P2 V2 by gamma minus 1. We have just changed the signs. We have bring this one in the front as the sign is changed, and this one behind, and this is the formula for work done for adiabatic process. For polytropic process, the polytropic law is P to the power n is equal to constant, where n is polytropic index and n is greater than 1 but less than gamma always. So the work done formula is given by P1 V1 minus P2 V2 by n minus 1. That's it. For polytropic process, it's P1 V1 minus P2 V2. Right? We have proved this. We have calculated the work done for different processes like constant volume, constant pressure, constant temperature, adiabatic process and polytropic process. We have calculated the work done for these processes, and if you find this video helpful, do like, comment and share the video, and don't forget to subscribe my YouTube channel AB Study Circle. Thank you.